Hey, this week we're shifting gears a little bit. We did 2 weeks of differential calculus, and now we're going to do basically the opposite, which is integral calculus. Okay, so the things we're going to work on this week are defining integrals, which are also called more or less interchangeably into antiderivatives. We're going to calculate integrals of different functions. Basically the same thing we did with derivatives we're going to do with integrals. So we're going to do products, quotients, sums and differences, exponents, logs, and the integral equivalent of the chain rule, which is integration by substitution. And we're going to attempt and succeed to understand the relationship between integrals and the area under a curve. And finally, we're going to apply all of this to real-world problems. Speaking of real-world problems, okay, we're going back to Yardley, Pennsylvania again, which you've probably figured out is my hometown, which is why I keep mentioning it. So we are estimating that the population growth of Yardley is dp dt, or p prime of t, equals this guy, okay, which is 48e to the negative 0.05 t divided by 4 plus 8e to the negative 0.05 t, whole thing squared. Okay, we're estimating that the growth rate is that many million people per year. And what we want to know is what is the exact population at the 10th year of this growth. Okay, so we have the rate, but we want to go backwards and find the population. Okay, kind of the opposite of what we did before. Before we started, we did population, and we wanted to know the rate. Okay, speaking of opposites, the opposite of a derivative is an integral or an antiderivative. Okay, just like the opposite of addition is subtraction, the opposite of multiplication is division. Okay, everything has its opposite. You can think of this as the bizarro derivative, if you like. Okay, symbolically, the sign for an integral is like a stretched out S. Okay, so in the simplest way of looking at it, and purists would obviously argue this point, but the integral of lowercase f of x dx is equal to capital F of x plus c, where c is a constant, which is another way, the opposite way of saying that the derivative of capital F is going to be lowercase. So they're kind of opposite, they undo each other. Okay, and that's important. It's important that if you do this correctly, if you take the derivative of both sides, you get a tautology. You get f of x, capital X, f of x equals capital F of x, which is the same because the derivative of a constant is 0. So what you need to know for integrals is not to forget that constant term. If you have an indefinite integral, you have that constant term. Okay, and the rules for finding integrals are exactly the reverse of the rules for finding derivatives. Okay, the power rule, if you remember that for derivatives, the power rule was to decrease the exponent and throw it in front. Here, you increase the exponent and you divide by it. Okay, so the integral of x to the 5th would be x to the 6th over 6 plus c, your constant term. Okay, derivatives involving constants times functions is going to be just, you could pull the constant out. Okay, I'm sorry, integrals, because it's just like derivatives. Okay, you can just pull the constant term out front and multiply that later. Okay, so the integral of 5x squared dx would be 5 times the integral of x squared dx. Okay, easy enough. Same thing, nothing too complicated about sums or differences of integrals. The integral of f of x plus or minus g of x dx is just separately the integral of f of x dx plus or minus the integral of g of x dx. Okay, another important one and a specific case, and just for symmetry's sake, we did this with derivatives. With integrals, the integral of 1 over x is equal to the natural log of x plus c. Okay, so the integral of x to the negative 1 dx is the natural log of x plus c. Okay, exponents, again, same but opposite as derivatives. If you remember the derivative of an exponent, you kept the exponent by itself and then you just multiplied by the argument of the exponent. Okay, same thing here but opposite. You just divide by it. Okay, so if you look at the example, the integral of e to the 5x dx would be e to the 5x over 5. Okay, and to check that you're right, obviously, you could take the derivative of what's on the right and you better get what's on the left. Okay, so again, integrals and derivatives undo each other. Okay, and similarly, for logarithms, okay, you have the integral of a to the kx. Okay, and this is not to confuse you, sorry about that, I should have done this earlier. Here you have the integral of x to -1 dx is equal to the natural log of x. Here you have a certain number, okay, to a power, and that is going to give you the number to the same power, okay, divided by the natural log involving the exponent there, okay? Don't be confused by this. I just put this out there so you can understand the difference between this guy at the bottom and this guy at the bottom, okay? Just understand that, and you're always going to have these rules in front of you. It's nothing that you have to memorize. It's just stuff that I really need you to understand. Okay, and again, with a log, be careful. Don't confuse the exponent with the base number. Okay, the base number there is 5. The exponent is 6x. Just make sure you get those guys straight. That's the only reason I included it there. Okay, so what you noticed is what I gave you was stuff with relatively simple arguments. Okay, the arguments here were like e to the 5x, x to the 5th, 5x squared. Okay, nothing too complicated. What happens if I give you something like this? If I ask you for the integral of 5x squared plus 4 times 10x dx. Okay, things do get a little bit hairier there. Okay, and this is the correlate to the chain rule. Okay, if you remember, we were doing differential calculus all of 2 weeks ago. If you had a complicated argument, what you could do is just substitute in and say, okay, I'm going to call this guy u, and then we're going to break it down by saying that dy dx is du dx times df dx. Okay, we're going to do that again. Okay, we're going to do basically the same type of approach. Okay, you're going to rewrite it as something a little more palatable, and then you're going to back substitute. Okay. So we had 5x plus 4 cubed times 10x dx. Okay, what do you want to see is you want to see what does this look like? If I were to substitute in for something, how could I put it in a form that I can really work with in a lot easier way? Okay, there's no rules that say you have to do, when you get this, you have to do this. You want to really do this by feel. So what does this really look like to you? And if not, can I get it into a form that's a little more doable? Okay, this really looks like u to the n du. Okay, where your u is 5x squared plus 4, and your du is going to be the derivative of that dx. Okay, so in this case, and I gave you a nice pretty example here, if we let u equal 5x squared plus 4, okay, what is the derivative of that? Okay, the derivative of 5x squared plus 4, and this is actually from 2 weeks ago, the derivative of 5x squared plus 4 is just going to be 10x dx. Okay? And the reason where that dx comes up is the derivative of u is really du dx, but what we're doing is we're taking that dx and we're multiplying it by both sides. So we're saying du dx equals 5x squared, sorry, du dx equals 10x, where du itself is equal to 10x dx. Okay, that's where that dx comes into play. Okay? And it's lovely because we already have that there. So if you look at what's here, whoops. Okay, if you look at what's here, we have 5x squared plus 4 as our u, and we need our du to be 10x dx, and lo and behold, there is our 10x dx. So if we substitute it in as u equals 5x squared plus 4, what we have is the integral of u cubed du. Okay? Take a moment and just make sure you can assure yourself that that's the case. Okay, where we substitute it in, we have the integral of u cubed du. And the solution to that, it's pretty simple. Okay, we know the integral of u cubed du is u to the 4th over 4 plus c. Okay, and now the only step that remains is we have to back substitute. Okay, so where we have a u, we put in 5x squared plus 4 because that's how we defined u, and that gives us our answer. Okay, and clearly not everything is going to be that easy. Sometimes it's going to take kind of a hop, skip, and a jump to get yourself into a position where you have something that's more recognizable. But general rule, not always the case, but general rule, you want your u to be either something raised to a power or something in the denominator, because if it's something in the denominator, if you remember, going up here, if it's something in the denominator like that, if it's 1 over u du, then your answer is going to be natural log. Okay, or you want it to be an exponent, because the derivatives or the integrals of exponents are really quite simple. So if you can get it in one of those three forms, you're in pretty good shape. But the real trick becomes manipulating things so that the du that you have is what you need. Okay, so let's look at a slightly more complicated example here. Okay, the integral of x squared plus 1 over 2x cubed plus 3x dx. Okay, not so easy to do. Because what we don't really have is we don't really have a quotient rule with integrals. That's kind of the problem. This is something you have to make up. So what we have looks sort of like it could be, and this is something you'll kind of learn with experience, if the exponents in the denominator are higher than the exponents in the numerator, then what you have might be something of the form the integral of du over u. Okay, in other words, if it's possible that the derivative of the derivative of what's in the denominator is actually the numerator, then you probably have du over u. So if we let u equal the denominator, 2x squared plus 3x, then we need our du to be 3x squared plus 3 dx. Okay, which is great, but we have in our problem x squared plus 1. Okay, so what we need to do is we need to figure out how do we get from what we have, which is x squared plus 1, to what we need, which is 3x squared plus 3. Okay, in this case, what we have is 1/3 of what we need. Okay, so if we put all of this back in, okay, we have 1/3 of du divided by u. Okay, and again, it's a constant, so we could pull it out. So we have 1/3 times the integral of du over u, and the integral of du over u is always going to be the natural log of u plus c. So if we back substitute, we get 1/3 times the natural log of 2x cubed plus 3x plus c. Okay, and again, this takes a little getting used to, and there's a little trickery involved, but the basic approach is you want to just get it in a recognizable form, and sometimes you need a little fudge factor, like in this case you needed that 1/3. Just need to make sure that you remember to put that in the problem. Okay, so what we've been working at so far are called indefinite integrals. And the reason why they're indefinite is we don't have limits on the maximum or minimum value of the integral. Okay, a definite integral is just an indefinite integral, except it's got that little thing above and below the elongated s, above and below the integral sign. Okay, so all that does is it defines the interval that we're looking at. And the practical consideration of that is if you have a definite integral, you don't need to do the plus c anymore. Okay, there's nothing to worry about that. Okay, and physically speaking, the definite integral of a function gives us the area underneath the curve defined by that function. So if we're looking at the simple parabola, say that 3 times fast, f of x equals x squared, and we want to know what is the area underneath that curve from x equals 1 to x equals 3, okay? All that is going to be is the definite integral of x squared dx from 1 to 3. So we know that the area underneath the curve is 8 2/3 units. Okay, that's what the integral tells us physically. Okay, so let's go to a little slightly less abstract example. Okay, remember that the derivative of distance was velocity. So the correlate here is that the integral of velocity will give us distance. Okay, so if you remember before we were looking at, I believe it was the distance traveled was, I think, s of t equals 100t minus 16t squared. Okay, and we said that s prime of t is 100 minus 32t. So if we wanted to go back and forth, if we had the velocity, 100 minus 32t, and we wanted to find the exact spot of it, we would take the integral of that. So that would be 100t minus 16t squared. It lets us go back and forth, which is the nice thing about derivatives and integrals. Okay, and really quickly, because again, this is an applied class, and I just want you to understand a few theoretical things, but the fundamental theorem of calculus really just codifies two things. It tells us what an integral is and how integration and differentiation are connected. So all it tells us is that the integral, and we kind of let off with this, of lowercase f of x dx from a to b is equal to f of x defined at b minus f of x defined at a. Okay, that's all it tells us. It tells us what we've been working on, but it says it in a much more formal way. Okay, so let's look back, now that we have all this great ammunition, let's look back at our Yardley, Pennsylvania problem here. So what we're looking for is P of 10. Okay, and we have dp dt here. Okay, so what does this look like? Okay, which of the major types of situations does this look like? A power problem, a log problem, an exponent problem? What does it look like? Okay, if you can see, and this is the cool thing about exponents, this is really just a u to the negative second du problem. Okay, now why is that? Okay, if you rewrite this guy as 4 plus 8e to the negative 0.05t to the negative second times 48e to the negative 0.05t, then it really looks like u to the negative second du. And why is that the case? That's the case because the derivative of an exponent is the same exponent times a certain constant. Okay, so here if we let u equals 4 plus 8e to the negative 0.05t, then what is our du going to have to be? Okay, the derivative of u here is going to be negative 0.4 e to the negative 0.05t dt. Okay, so just make sure you can see why that's the case. If you take 8 times negative 0.05, it gives you negative 0.4. Okay, so that's going to be, and the derivative of a constant of the derivative of 4 is 0. Okay, and what we actually have in the problem is we have a 48e to the negative 0.05t. Okay, so how do we rectify that? Okay, if you remember a few slides ago, we kind of have to put in a little fudge factor there to make things fit. Okay, so what do we need to multiply negative 0.4 e to the negative 0.05t by to make it fit with what we have in the problem? Okay, we have to multiply it by a negative 120. Okay, so what we really have in this problem is we have u to the negative second times a negative 120 du. Okay, when we do all the back substituting, that's where all that comes into play. Okay, so just make sure this makes sense to you. Okay, I'm going to pause for a second so you can kind of scratch your head and think about why this is the case. Okay, I know you've got it now. So the integral of this guy would be, again, you could pull out the constant, so it would just be negative 120 times a pretty simple function. Okay, negative 120 times u to the negative second du. Okay, and the solution to that is going to be 120 u to the negative 1 divided by negative 1, which is just 120 times u to the negative 1. Sorry, I missed a minus sign there in the second to last step. Okay, but the answer to that is going to be 120 times u to the negative 1. And if you remember what we defined u as, we said that u is going to be 4 plus 8e to the negative 0.05t. So the answer is going to be 120 times u to the negative 1, which is 120 divided by u. We get 120 divided by 4 plus 8e to the negative 0.05t, which, if you remember from 2 lectures ago, was exactly where we started from. Okay, and because we're looking for this at a definite point, we don't need to have a constant there. We don't need a plus c. So at t equals 10 years, our population is 13.6 million people. So I really just did this example not because I like to talk about Yardley, Pennsylvania, but because I like you guys to see how differentiation and integration really just are the opposite of each other and how they fit together. Okay, so that's it. And if you have any trouble understanding what we did with the substitution and the u values and all that, please ask. Otherwise, I will see you next week.